Yesterday, we extended the idea of refraction, the idea of the bending of light due to a change in medium, to the concept of lenses, curved lenses specifically. Curved lenses bend light, and they do it in a very purposeful way so that we can see a certain image, an image that we want to see. Sometimes we put a curved lens in front of our eyes. We may put a curved lens in front of our eyes to spread out the light so that it doesn't converge quite as quickly. It converges a little bit further back on our retina. Maybe we put a lens in front of our eyes to bring the light together, just in case the light is converging behind our retina. In other words, maybe we're nearsighted, maybe we're farsighted, maybe we need a convex lens, maybe we need a concave lens, depending upon what we can see and what we can't see. Maybe we just want to magnify text, use a magnifying glass. Okay, maybe we want to project the image that literally you see right now from the projector on the ceiling to the wall. Maybe we want to watch a movie and we project the image through the lens of the movie theater projector. Lenses, any way you look at it, bend light in a purposeful way to produce a certain image. There are two general kinds of lenses. The first one we call a convex lens. A convex lens is also known as a converging lens. Converging because, as we said yesterday, light rays converge. Light rays come together. Oops. Light rays come together or converge at a place that we call the focal point. That is, if those light rays are parallel to the principal axis, they come together and converge at the focal point. If you have, on the other hand, a concave lens, which is also known as a diverging lens, then we have just the opposite taking place. Light rays that are parallel to the principal axis don't come together at the focal point. They actually diverge or they spread apart from the focal point. And we'll draw a diagram of that in just a few moments here. Now, when we're drawing a ray diagram to try to determine what the image looks like from a convex or a converging lens, there's a whole bunch of rays that we could draw, but there's only two that we ever really need to draw. The first ray is going to be that ray that comes off the top of the object, reflects off of the top of the object, and reflects parallel to the principal axis. We know what happens to that ray, right? Where does it refract? Where does it bend when it hits that lens? The demonstration that I just did should illustrate that, right? All rays of light that are parallel to the principal axis refract or bend and go through which way? Which point? The focal point. They all go through the focal point. All of them that are parallel to the principal axis go through the focal point. This one does too. But I'm not going to draw that one, because that's not coming off of the object. This is the first ray that I want to draw. This is the first ray that's going to help me determine what the characteristics of this image look like. The second ray that I'm going to draw goes from the top of the object down through what we call, what's this point in the middle of the lens called? Yep. The optical center. Good. And where's it going to go from the optical center, Simon? So like this. Where does it go? This one bends, right? When it gets straight here, it bends and goes down through the focal point. But the one that goes to the optical center doesn't bend. It just keeps going straight. The image is going to be formed right here where these two intersect. The bottom of the image at the principal axis, the top of the image down here where they intersect. The characteristics of this image would be what? Okay, number one, larger, smaller, same size. Let's compare the image to the object. Is the image bigger, smaller, or the same size as the object is? Smaller. So we're going to say that the first characteristic is that it's smaller. Second characteristic, is it right side up or upside down? In other words, is it upright or is it inverted? It's inverted. It's upside down. And the third one, real or virtual. Remember, real can be projected onto a screen. We just did that in our demonstration, right? We just projected it onto a screen. In that situation where the object is far off. It's a real image. But how do you know that it's a real image? Okay, when I'm actually doing the experiment and shining it onto a card, I can see that it's projected onto a screen, that it's a real image. But when I'm drawing the diagram, how do I know that that could be projected onto a screen? What tells me? What do you see on the board right now that tells me that this could be projected onto a screen, that this is a real image, Tom? Okay, the two lines meet, good. But sometimes, even when they meet, it's not a real image. It's a virtual image. Caitlin? Good. They're solid lines. When dotted lines intersect, then we've got a virtual image. It couldn't be projected onto a screen. You can see it, but you got to look through the lens in order to see it. Let's take a look at one more ray diagram here, right here. This is when we have our object really, really close to the lens. First ray, same as the first ray was before. Top of the object parallel to the principal axis down through the focal point. Second ray is going to go from the top of the object down through the optical center. It's going to keep going. They don't intersect. What does that mean? We have no image? No, we are going to have an image. So how do I draw these intersecting if they're not intersecting right now? What am I going to do to it? Let's extend them backwards. Let's extend the refracted ray, the bent ray. Whoops, look at that. They intersect back there. There's my image. Characteristics of this one. Is the image larger, smaller, or the same size as the object? Devin, larger, smaller, same size? Larger or bigger? Sometimes your textbook calls it enlarged. Doesn't really matter what you call it as long as you recognize that it's bigger. Second one, upside down or right side up? Is the image upside down or right side up? Right side up. I call that upright. There's all kinds of other terms that you could call it. It doesn't really matter as long as you recognize what it means. Now, in the demonstration that I showed you, you clearly saw on the card on the screen that the image was upside down. The Canadian flag was upside down. 3, is it real or virtual? Could it be projected onto a screen or not? It's virtual. How do you know that? Good. Dotted lines intersect. That tells me that it's a virtual image. Now, you guys filled out all 5 of the possibilities of ray diagrams for converging lenses yesterday. Today, you're going to fill out all 5 of them for diverging lenses. The good news is they go quicker. The reason they go quicker is because they all end up being pretty much the same. The first situation that I have here for a diverging lens, diverging or concave. Concave means caved in, right? They caved in the middle, thinner in the middle than it is at the edges. The first situation that I have is when the object is well beyond the focal point. In fact, it's well beyond 2f. Notice in this case, notice for the converging lenses, the focal point is on the right-hand side. It's on the side opposite to the object. For this one, the focal point is on the same side as the object. The first ray here is going to go parallel to the principal axis from the top of the object, just like it did before in the last one. Where do you think it goes? Down here? That's where it went for the converging lens, right? It's not where it goes for the diverging lens. Scratch that one out. Down here? Shouldn't it go through the focal point? No, that would be a mirror, right? That would be a converging mirror because the rays would converge at the focal point, but they would be reflecting off of it instead of refracting. Where's it going to go? Spread apart, somebody said? Who said that? Is that you? Okay. Yeah, they're going to spread apart, but where are they going to spread apart from? What's the point that matters here? Where are they going to diverge away from? It's staring you right in the face. Bless you. It diverges away from the focal point. So in other words, it's like there's a line drawn right here all the way to the focal point. Instead of going down through the focal point like it did with converging, it spreads out or diverges away from the focal point. Now the second ray, oops, bless you. The second ray is going to go from the top of the object down through the optical center again. And you know what? It's going to do exactly the same thing as it did for a converging lens. It's going to keep going straight through. They don't seem to converge anywhere. So let's extend them backwards. Let's extend the refracted ray, the bent ray, backwards. Okay, the second ray that I drew, if it goes straight through, the refracted ray would be extended backwards this way. The other one would be extended backwards this way. Look at that. I got two dotted lines intersecting there. There's my image. You know what? The reality is, if you don't draw this one, extend it backwards, you're going to still get them intersecting in the same place. I just want you to recognize that it's not really a solid line and a dotted line intersecting. It's really two dotted lines intersecting. It's really the extensions of the rays that are intersecting at that point. All right, what do you know about the characteristics of this image? Number one, is this image larger, smaller, or is it the same size as the object? Kirsten, is it larger, smaller, or same size? Take a look at this image. Look at its height, and then take a look at the object. Look at its height. Is the image bigger or smaller? Smaller. Yeah, good. The image is smaller than the object is. Is the image right side up, or is the image upside down, Daniel? It's right side up. We're going to say that's upright. And finally, is the image real or virtual? Maria, think you know this one? Why would you say it's virtual? Good. It's virtual, which means it can't be projected onto a screen. We could see it, but we'd have to look through the lens to see it, right? I have to put my head right here, look through the lens, and I'd see it then. Couldn't project it onto a screen. But we know that, as Maria said, because it's two dotted lines that intersect. Smaller, it's upright, and it's virtual. I'm going to draw the next one for you as well, and then I'm going to have you guys draw the last three. Remember what this looks like as we draw the next one, okay? The next one's going to look remarkably similar to that. First ray goes from the top of the object to the lens. It's going to refract away from the focal point. It's going to bend away from the focal point. When you're drawing that yourself, take your ruler. Take your ruler and take your ruler, extend it way back to the focal point, just like this. And then draw your line like this. Okay, as if it's going away from the focal point. The second ray, the top of the object down through the optical center. They don't intersect, so let's extend them, both. This one gets extended backwards like this. This one gets extended backwards like this. Ends up being right there. How does that compare to the one we just did? Well, it actually looks to be a tiny bit bigger than the one that we just did, the image, but it's still smaller than the object. It's still upright, and it's still, as Maria said from the last one, virtual, because dotted lines intersect. We could not project that onto a screen. What I'd like you to do right now after you finish copying this is to draw the next three yourself. The good news is when you draw the next three, the same two rays are what apply to all three of them. The same two rays as you've already drawn for these two are the same two rays that you draw for the next three as well. So no tricks, no changes. You may find that the image looks a little bit different than it does for the two that we've just drawn, but it's going to be for the most part the same. If you get something dramatically different, then you should try again. Okay, I'll take a walk around and watch you as you're doing it. Put up your hand and ask me if you're having trouble with it, and then we'll draw one or two more when we're finished there, okay? You've had a chance to do this now. Let's try one more ourselves here. Let's do this one right here. Okay, let's do this one. First ray goes parallel to the principal axis, then it refracts up away from the focal point. The second one goes down here, down through the optical center. Let's extend both of these. This one gets extended back like this. This one gets extended back like this. The image formed is going to be right here where the two rays intersect. Now, if you look at this one compared to the two that I already drew, you can see that the image is quite a bit bigger than the image was before for these two that I already drew. But the characteristics of this image are still going to be the same. It is still smaller than the object. It's bigger than the last image was, but it's smaller than the object, and that's what we're comparing it to. It's still upright. And Maria, it's still what? Real or virtual? Still virtual. We know that because dotted lines intersect. It's virtual. It means that we cannot project it onto a screen. We can see it, but we have to look through the lens in order to see it. All right? Make sense? All right, well, here's the thing. The ray diagrams that we've just drawn are important. You may have to draw a ray diagram in order to get some characteristics of an image for your diploma exam. But you won't actually have to draw a ray diagram on your exam because you can't, right? It's a multiple choice question. The questions that you're more likely to see are, what are the characteristics of the image produced when the object is located this far away from the lens? Or, what are the actual distances involved? What are the numbers involved? Well, in order to give us a question involving numbers, we have to have an equation or two. So I'm going to write down two equations right now that apply to this whole lens analysis. The first one we call the lens equation, the thin lens equation. The thin lens equation, you might like this, you might not like this. It involves fractions. 1 over f is equal to 1 over dO plus 1 over di. F stands for the focal length. The focal length is the distance from the lens, from the center of the lens to the focal point, the focal length. dO stands for the object distance. And the object distance is the distance from the lens to the object, wherever we put the object, that right side up solid arrow that we do our lines coming from. di would be the image distance. That's the distance from the image, where those lines intersect. Right side up or upside down image, from the image to the lens itself. Now, what units should we use here? Well, go ahead and use meters. Go ahead and use centimeters. Go ahead and use millimeters. Go ahead and use kilometers. Why doesn't it matter here? Why doesn't it matter what units you use? Yep. Good. It's the same in every term, Caitlin, so they cancel it. Good. Typically, what we're going to use here is actually centimeters, because it's usually the most convenient one to use, given the distances that we're usually dealing with. But there's nothing wrong with, listen, if it confuses you, centimeters, we never use centimeters. I want to go with meters. Then go with meters. Convert it to meters. That's fine. Okay. Meters always works. In this case, centimeters does as well, but meters will always work. There's another equation as well that we call the magnification equation. Because m is equal to hi over ho equals negative di over do. We already know what di and do mean, the image distance and the object distance. What do you think hi stands for? What does hi stand for? Di stands for the distance from the lens to the object, sorry, to the image. Hi would stand for, Maria, the image height, right? How tall the image is. And again, we can use centimeters or meters, whatever we want for this, as long as we're consistent. This one, of course, is going to stand for the object height. And m will stand for, m stands for the magnification. The magnification is a ratio. It's It's a ratio of how big the image is as compared to the object. If the number works out to be 2, then that means the image is twice as big as the object. If it's 0.5, then it's half as big as the object. Okay, if the magnification is 3, then the image is 3 times bigger. If the magnification is 0.25, then the magnification is then the image is 1/4 the size of the object. There are no units for magnification. It's not centimeters, meters, it's nothing. The units cancel out. HI over HO. Centimeters over centimeters gives me nothing. Now, they're not that hard. Okay, the fractions might bother you a little bit, especially in the first equation. But if you're not good with fractions, I got a nice out for you. Okay, a nice way to do this on your calculator to save you the bother of worrying about fractions. If you're good with fractions, that's great. If you're not, don't panic. Before we do any numbers, though, before we put any numbers into these equations, we have to identify a sign convention or some sign conventions. In other words, what's positive, what's negative. Because all of these variables, F, DO, DI, HI, HO, and M, can all be positive in some circumstances and negative in other circumstances. Let's create a little chart here to identify when these are positive and when they should be negative. Let's first look at the object distance. No, actually, let's look at F, the focal point. The focal point is positive when you have a real focal point. Now, when do you have a real focal point? Let's go back to our ray diagrams. Do the rays really converge at this focal point right here? They don't. They diverge away from it. Do the rays really converge at this focal point? Where are we here? Right here? Yes, parallel rays really do converge at that focal point. So this is what we call a real focal point when we have a converging lens. This is what we call a virtual focal point when we have a diverging lens. So we're going to fill this box in by saying a real focal point occurs when you have a converging lens. F is going to be negative if you have a virtual focal point, and that occurs when you have a diverging lens. DI is positive when you have a real image. Sometimes you get a real image, sometimes you get a virtual image. It's positive when you get a real image. It's negative if you get a virtual image. DO is positive when you get a real object. And it's negative when you get a virtual object. The good news is, for us in Physics 30, the object will always be real. Always. There are circumstances in which you can have a virtual object. That won't happen for us in Physics 30. So for us, DO will always be positive. And DO will never be negative. Now let's look at HO and HI. Notice I've changed the color there. There's a reason I've changed the color, because the pattern changes a little bit. HO is positive, not when we have a real object. HO is positive when we have an upright object. An object that's right side up. And it's negative when we have an inverted object. HI is positive when we have an upright image. And it's inverted. It's negative when we have an inverted image. So the blue ones, F, DO, and DI, they're positive based on whether they're real or virtual. The green ones, HO and HI, are positive and negative depending upon whether they're right side up or upside down. There's one more here that doesn't really fit. It doesn't really fit into the table. It's the magnification. The magnification is positive when the image and the object are both either upright or inverted. In other words, they're both on the same side of the principal axis. They're both like this, M is positive. Or they're both like this, M is still positive. If the object is like this and the image is like this, then M is negative. If the object is like this and the image is like this, then M is negative. When they're on the same side of the principal axis, M is positive. So we'll say M is positive when object and image are on the same side of the principal axis. They're both either right side up or they're both upside down. Gives me positive. If one's upright and one's inverted, then it's going to give me a negative. So we don't have time to do a problem with this, but you can answer a couple questions for me before the bell does go. If I have an object that's right side up and an image that's upside down, M is going to be what? Negative. If I have a magnification that is positive 0.5, what does that tell me about the image?
Leah Acton, Kennedy Armstrong, Ian Booth.
It tells me that it's half the size of the object, and it tells me that it's on the same side of the principal axis. What if I have a magnification that's negative 0.5?
Victoria Jones.
It's half as big, but it's flipped over. The image would be flipped over relative to the object. Does that make sense? Okay, we'll pick up where we left off here tomorrow. Have a good night, everyone.